Hi everyone, welcome to the presentation for our paper Understanding Masked Autoencoders via Hierarchical Latent Variable Models. This is a joint work with a group of wonderful people at CMU. Masked autoencoding is a canonical self-supervised learning paradigm for visual representation learning. The procedure is fairly simple. We first divide the image into patches and mask out a fraction of the patches randomly. We feed the unmasked patches into the encoder, which is often a vision transformer, to obtain the representation of the image. With this representation, the decoder predicts the missing patches masked out at the beginning. MAE pre-trained encoders can be fine-tuned for various vision tasks, including classification, detection, image segmentation, etc., and achieve the state-of-the-art performances consistently. Empirically, it is all great and awesome, but many questions remain unanswered on the theoretical front. Specifically, how should we understand MAE's efficacy in so many vision tasks? How does this emerge from the MAE pre-training? Also, empirically, hyperparameters of the MAE pre-training, including the masking ratios and patch sizes, heavily influence the model performance. How do these hyperparameters impact the learned representation, and how can we derive some principles for more informed hyperparameter tuning? In this work, we address these points from a latent variable identification perspective. First, we formulated the data generating process for images with a hierarchical latent variable model. The hierarchical structure captures the intuition that various levels of statistical dependence between the pixel patches. For instance, patches belong to a single object are typically locally correlated, such as the cloth and the rod that make up a sail in the figure. In contrast, patches belonging to distinct parts have a more hierarchical dependence, such as the sail parts and the boat body in the figure. So for our theories to follow, we also make some assumptions on the structure and the data generating process.
Now we introduce the main theoretical results of our paper. Our first result suggests that there is a one-to-one correspondence between each specific mask and a set of latent variables in the hierarchical model. This means that a specific set of variables can fully capture the statistical dependence between the masked part and the unmasked part in the image. Our next result suggests that for each mask, MAE can recover the corresponding true latent variables in the hierarchical structure. For example, in the figure, Z1 is the high-level latent variable, which represents the high-level dependence, while Z2 through Z4 are low-level latent variables, which model low-level dependencies. To reconstruct the masked patches X1 through X3 from the visible patches X4 and X5, MAE has to leverage the high-level statistical dependence between them by recovering the high-level latent variable Z1. Given that MAE can recover high-level information, how will the masking hyperparameters change the representation quality of MAE? We are particularly interested in the masking ratio and the patch size. From our analysis, we show that conservative masking with lower masking ratios and smaller patch sizes can make MAE capture low-level information only, as suggested by subfigure A, where the low-level latent V3 is identified. Counterintuitively, we also show that aggressive masking, such as setting masking ratio to 0.9, may also lead MAE to capture low-level variables, as shown in subfigure B. An ideal masking, such as the one in subfigure C, should force the MAE model to capture the high-level Z2 variable. In general, we find that learning high-level representations is hard with random masking. We validate our theoretical understanding by running a range of empirical analysis. Here we illustrate two of them. The figure on the left shows the reconstruction evaluation of MAE. The y-axis are the structural similarities between the reconstructed image versus the original image. Higher metrics suggest higher structural similarities. The highlighted red circles suggest higher masking ratios and larger patch sizes capture high-level structural information better. Next, we show self-attention visualization on the right panel, where the top two rows are attentions on the COS token, and the bottom two rows are attention on the selected object tokens, such as a dog nose or a cat chin. The highlighted red rectangle suggests that higher masking ratios and larger patch sizes better capture high-level object information, as suggested by the global activations in the heat maps. However, from the highlighted orange rectangle corresponding to the extreme masking ratio 0.9, we observe that extreme masking can induce the model to capture low-level information, as shown in the activation concentrated in local areas in some of the heat maps. In conclusion, our work formulates the data generating process of natural images as a hierarchical latent variable model and show that MAE can learn meaningful representations by provably identifying the true latent variables in the hierarchical model. Our theory provides insights into the effect of masking ratios and patch sizes on the representation quality, and show that in general, higher masking ratios make the model learn higher level semantics, although extreme maskings can make the model only capture low-level information. Lastly, we argue that learning high-level representations in general is hard with random masking. We hope our work could provide insights for empirical improvements and theoretical understanding of the masked autoencoders. Thank you very much.